Okay, General Chemistry 2 class. This is Dr. Rowley coming back with our second lecture on thermodynamics. And yeah, by the way, if it looks like I haven't changed clothes since Wednesday, well, I haven't. Actually, I'm recording both these Wednesdays and Fridays lectures on Wednesday, so that's why there's a lot of the same. We're going to continue with everything you need to know about thermodynamics. So a couple of things for Friday. Let's say this is Friday, then Alex chapter 15 is due tonight. Make sure you work on that. I will have this lecture posted probably on Thursday, so whenever you see that, don't forget the Alex Open Pi. Next week's lab, no, it's not nuclear chemistry. Shoot, that is, forget this, no nuclear chemistry. It's actually the thermodynamics lab. It's the new thermodynamics lab, which is available on Moodle. So I posted it on my lab Moodle sites. Your lab instructors should be posting it on theirs, so you'll have plenty of opportunity to see it before the weekend. I will also post it on the class Moodle sites as well. I haven't done that yet. But it's not nuclear chemistry. That's the new thermo lab. And we will actually have hard copies when you come to class or come to lab next week. Hard copy printed thermo lab handouts. So you'll have plenty. You can read it. You don't feel like you have to print it, in other words. Let's see, finish quiz 3, yeah, worksheet 9. So this is all the rest of the same. I didn't bother updating all the stuff from Wednesday. But we do have some new to spare because this is, after all, what I care about most. Looking sharp is easy when you haven't done any work. Makes you think. The early worm is for the birds. And I'm teaching 8 o'clock classes. Great. In the battle between you and the world, bet on the world. Because we're all in this together, but there's always room for one less. Wow. Dreams are like rainbows, only idiots chase them. It's your only hope for success, really. All right, here we go. Chapter 15, Thermodynamics, Part 2. Part 2 of 2. Here are the objectives for today. We are going to understand the entropy changes in the universe, the 3 laws of thermodynamics, and Gibbs free energy. Gibbs free energy. We're talking about free energy today. We already talked about entropy. This is the only slide I think I'm showing you from Wednesday's lecture. So remember that entropy is a measure of disorder. The greater the entropy, the greater the disorder. I guess that's not the only slide. Okay. Here are the 3 laws, 3 of the laws of thermodynamics. There is a 0th law. Law number 1, matter is neither created nor destroyed. Remember we talked about binding energy in the nuclear chemistry chapter? We didn't calculate binding energy, but we did walk through it. The mass difference between the sum of the individual protons and neutrons is greater than the sum of the mass of the individual nucleus. That mass difference is the energy, the binding energy, the glue that holds that nucleus together with all those positive charges. Matter is neither created nor destroyed, but it can be converted into energy, and energy can be converted into mass. The entropy of the universe increases in a spontaneous process. Remains constant for an equilibrium process. We're going to be touching on equilibrium and introducing that a little bit more. We're throwing a little bits and pieces of equilibrium at you as we go along. We're going to hit that in the chapter after this. The entropy of the universe increases. In other words, this is the same way of saying what I mentioned before, is that entropy happens. The natural state of the universe is toward increasing disorder. You leave that can outside, it's going to rust, or it will change. There will be spontaneous processes. Entropy takes over, and that's what happens. The third one is you can have a state where there is zero entropy. And that is if you have a perfect crystal at absolute zero. Perfect alignment of atoms with zero vibrations. The atoms are just sitting there. There is no entropy. You take that perfect crystal, you warm it up a little bit. Those atoms start moving. That's entropy. Gibbs free energy. This is really what we want to focus on today. Whether a chemical reaction is spontaneous or not depends on two things. Specifically, it depends on enthalpy and entropy. If you're not clear about enthalpy, go back and review that chapter in Gen Chem 1. That's what I get for talking so much today. Enthalpy is the energy that's involved when bonds are broken and then reformed. That enthalpy difference, we often call it heat. It's heat of reaction. Entropy is disorder. Enthalpy has units of kilojoules. Entropy has units of joules per Kelvin. Oh, I like that green. That's a nice color. Combined, they give us the Gibbs free energy equation. And in this particular set of slides, I'm trying to keep delta G represented in red, delta H in blue, and delta S in green. This is the connector between Gibbs free energy, enthalpy, and entropy. So you see, we're defining free energy in terms of these two. Remember that this is joules per Kelvin. So this joules per Kelvin, think of it this way. Let's say we've got an iron bar at room temperature, at 20 degrees C. You have that iron bar at 20 degrees C. It has some total entropy. The change in entropy is in joules per Kelvin. As we raise the temperature 1 degree Kelvin, there is an incremental entropy increase. So you see, that's why delta S is temperature dependent. What about delta H? Is delta H temperature dependent? So let me pause. We have a chemical reaction. Remember that iron and oxygen one? Iron and oxygen goes to Fe2O3. Big entropy change as we go from reactants to products. What happens if we take that reaction and change the temperature? The temperature matters for that. The temperature matters. So entropy changes incrementally per degree. Delta H, think of it this way, it's the bond energy. So let's say we have a hydrogen-hydrogen bond. The energy to break that bond doesn't really depend on the temperature. The energy of that bond is almost the same no matter what temperature you're at. Now, obviously, you can raise the temperature and break that bond, perhaps, if you raise it high enough. But enthalpy is not temperature dependent, entropy is. And that's why we have this T times delta S. The units, kilojoules, kilojoules, kelvins times joule per Kelvin. So T delta S gives us units of joules. Kilojoules, joules, we have to make sure that we do some conversion of joules to kilojoules somewhere along the way. Because joules, remember, that's a pretty small energy amount. Kilojoules, 1,000 joules. Okay, so really what is Gibbs free energy? By the way, this is named after Willard Gibbs, famous thermodynamicist who really developed these concepts. Free energy is the total amount of available energy to do work. Let's look at this reaction. Hydrogen and oxygen react to form water. Hydrogen and oxygen react to form water. If you take a hydrogen balloon and you light it, the hydrogen reacts with oxygen in the air to spontaneously form H2O. We know that that's an exothermic reaction. Remember the Hindenburg, exothermic reaction. For this reaction with these coefficients, minus 242 kilojoules, that's how exothermic it is. Delta H says this reaction wants to go. Remember for that kinetics diagram where we have the big hump? That means the energy of the reactants is up here, the energy of the products is down here. That big energy gap That's 242 kilojoules, 241.8. That's the difference. That's pretty big. Entropy, on the other hand, says we're going from 1 to 3 moles of gas to 2 moles of gas. 3 moles of gas to 2 moles of gas. That is creating more order. Delta S is negative. Delta S is negative by this amount because we can calculate it. You know it's negative just by looking at it, by inspection. We can calculate the amounts by looking up those values and solving it products minus reactants. So, does this reaction go? Well, let's see. Whether it goes or not, enthalpy says yes, entropy says no. Plug in the values if we're at 298 kelvins or room temperature, 25 degrees C. Plug in the kilojoules. Here is temperature times entropy. Here's our factor for converting joules to kilojoules. The enthalpy term is this. Combine all of this stuff and we get plus 16.9. Remember that the more negative delta H, the more exothermic it is. This is much bigger than this. This is the amount of energy available to do work. About 225 kilojoules exothermic. So what happens here is that enthalpy is driving this reaction. Enthalpy is driving this reaction. And because it's driving it forward, more order is being created along the way. Because the amount of order it's creating is not very big. This is the energy it takes to create more order by going from 3 moles of gas to 2 moles of gas. Delta G, this number right here, that is the total amount of energy available to do work. How are you doing with this so far? Great, I'm glad to hear that. Okay. So with this equation, by the way, here's what happens. The more negative delta, if delta G is negative, the reaction is spontaneous. If delta G is positive, the reaction is not spontaneous. Delta G is the ultimate determiner of whether a reaction is spontaneous or not. So if delta H is negative, that favors spontaneity. If delta S is positive, this becomes more negative. Minus a positive, more negative, that also favors spontaneity. So negative, positive, this will always be spontaneous no matter what the temperature. Sorry about that. Okay, if delta H is positive and delta S is positive, delta S favors going forward, delta H does not. So now, at higher temperatures, the greater this term, the greater the temperature, that's weighting the T delta S term, the more likely that is to be spontaneous. Okay, so in other words, if they're the same sign, delta H and delta S are fighting each other. And then if this is positive and this is negative, positive minus the negative, positive, that is not spontaneous at any temperature. Okay, let's look up this reaction now. Let's revisit this. We talked about this reaction with entropy. So we've already done this calculation to get minus 543.8. This is what we talked about on Wednesday, or in this case, earlier on Wednesday. So let's look up the values from the table. For iron, this is an element. For both delta H and delta G, standard, those are 0. For elements, oxygen and iron, both of them are 0. When we look up this, the enthalpy and free energy for standard free energies for Fe2O3, for iron 3 oxide, for those of you naming at home, these are the values that we get. For this reaction as it's written, this is the value of delta S, this is the value of delta H, this is the value of delta G. We calculated this products minus reactants. We can also calculate this number if we know these two and the temperature. This number should be equal to this delta H, minus temperature times this, T delta S. And that's what we're doing here. So if we know that from products minus reactants, what we just showed on the previous slide, this is the number we get. What if we take the numbers that we just got for delta H, delta S, plug it in, notice that we get 1482.3. This is 1482.0. They're not the same. Yeah, but they're pretty close. They're within less than 0.1% of each other. So are they the same? Absolutely. Within standard calculation error, they are the same. Okay. Now, how do we use this? Here we're given a different temperature. Can we calculate the free energy at a different temperature? Sure. 250 degrees C. This is a lot hotter than it was earlier. So if we increase the temperature, remember that delta S is negative. We're creating more order. So as we increase the temperature, what does that do? This is already a negative term. If we increase the temperature, that makes this more negative, minus a negative, more positive. Whatever this term is, as we raise the temperature, it's going to make the free energy, excuse me, less spontaneous. We do the calculation, 1360. Remember what it was for room temperature? It was around 1480. 1482. So this number was 1482 at room temperature, minus 1482. As we raise the temperature, it is less spontaneous. Is it still spontaneous? Absolutely, it's still big time spontaneous. Minus 1360 kilojoules, that is a pile of energy. Okay, we're actually almost done. Not quite, but we're getting almost done. I'm going to introduce this concept now. And this is what we are dealing with for non-standard states. We're not going to focus so much on this yet, this lower equation. I want to talk about this one for now. What do we do if we're not at 25 degrees C, if we're not at 1 atmosphere pressure, and if we're not necessarily at 1 molar concentration? This equation applies. This is the equation for calculating delta G when we are not under standard conditions. So we have, notice that delta G, no naught, no little zero, just free energy for a reaction, this is more realistic, is equal to the free energy under standard conditions plus R T natural log of Q. We're going to talk about Q in equilibrium, but we just want to introduce this concept right now. R is the 8.314 joules per mole Kelvin constant. T is the temperature in kelvins. This is an adjustment for temperature and concentration. Q fits in concentration right here. Okay, let me back up. All right, as we're approaching the end here, just a couple of thoughts. Q. I'm going to introduce this, I guess, we'll talk a little bit more about this now. For a given reaction, notice that we have K, there's Q. So I'm going to go back to this reaction. And I guess I'm going to write over here. So let me start with a different reaction here. Let's say we have H2 plus Cl2 goes to 2HCl. And let's say these are all gases. And let's say what happens. We talked about this, by the way, in kinetics. We had a fast equilibrium in kinetic mechanisms. We start with H2 and Cl2. They start reacting, they start producing this stuff, HCl. And this is now gas phase hydrogen chloride. You reach a point where this builds up, and then it says, hey, I'm going to go back where I came. So we end up with the two-headed arrow, which represents equilibrium. Remember that equilibrium is when the rate forward is equal to the rate reverse. We looked at this with regard to elementary reactions in kinetics mechanisms. Now, here's where big K comes in. Notice that little k was the rate constant. Big K is an equilibrium constant. Gas, gas, gas. For equilibrium constants, and this is true for the overall reaction, it's equal to the concentration of products, in this case, HCl, product, the concentration of products over the concentrations of reactants. It's like this. The products are in the numerator, the reactants are in the denominator. There's one more thing we have to do. This was not true for rate constants. This is true for equilibrium constants. The coefficients become the exponents. The coefficients for an equilibrium constant expression become the exponents. 1, 1, 2. 1, 1, if it's 1, we just leave it. But HCl is 2. That is an equilibrium constant. Let me back up. This is the equilibrium constant. This is an equilibrium constant expression. Equilibrium constant expression. This is going to be part of our transition from 15 to 16, chapter 15 to chapter 16. In an equilibrium, here's one more thing I'm going to throw at you before we move on. In an equilibrium constant expression, can we have molarity of a gas? Yeah, you can have molarity of a gas, moles per liter. Can we have molarity of a solid? We can have molarity of aqueous solutions. So for example, if salt is dissolved in water and it has a molarity, that is the concentration that goes in. There is a rule that only gases, so how many we have? Gases, liquids, solids, liquids. These are the 4 phases. Of the phases that appear in an equilibrium constant expression, gases, aqueous solutions. How do we do the molarity of a liquid? What's the molarity of water? Well, if we have a liter of water, how many moles is that? Well, a liter of water is a kilogram of water, which is 1,000 grams of water, which we can convert to moles. What if we have, but the thing is, the concentration of a liquid is a constant value. It's something that doesn't change. So we don't worry. We don't put liquids in an equilibrium constant expression because its concentration cannot change. And the same thing is true with solids. Let's say we dump a chunk of metal in a solution. Well, as long as we have solid there, it doesn't really have any defined concentration. It will have a constant value or constant concentration. But it's not something where the concentration of a solid can change. Gases and aqueous solutions are only part of that. So let's come to Q. Let's come to the equilibrium concentration for this. So K, let's write K for this reaction right here. Products over reactants. What is our product? Fe2O3. Fe2O3, it's a solid. Does the solid appear in the equilibrium constant expression? No. So this is just a 1. It's a constant. Any of the constants for those get rolled into K. It is a concentration that cannot vary because it's a solid. And iron is a solid. So it's concentrations of products over concentrations of reactants. These two are multiplied together. Excuse me, those two are multiplied together. We would multiply these together, but this is 1, and then we have the concentration of O2. This is a gas. And its coefficient is 3. Therefore, that looks like this. Is it weird? You look a little weird? It may look a little weird, but this is how you would write the equilibrium constant expression for this reaction. Products over reactants, you will only include things that are aqueous or gas phase. When you have K, K means that you have an equilibrium. K is at equilibrium. The reason we're going through all of this is to talk about Q. K is a fixed value. It is a fixed value at a given temperature. Q looks exactly like K. Q and K have the exact same form. Here's the difference. With K, you have a fixed value, you are at equilibrium. Q, same form, you are not necessarily at equilibrium. These numbers can be anything. That it represents equilibrium, but we're not at equilibrium necessarily. So let's go to this next to the last slide. Here we have Q. Here we have Q. Q is some non-standard set of conditions. Let's say all of our concentrations are 0.1 molar. Well, that factors in here. Products over reactants, coefficients become exponents. We work out Q. K is being at equilibrium. So what happens if we are at equilibrium? If we're at equilibrium, this delta G is 0. At equilibrium, this goes to 0 and this goes to K. So if this goes to 0, just delta G stays on this side, everything else goes on the other side, minus RT natural log of K. That's how these two equations are related. This is a useful equation for connecting equilibrium constant to free energy. Okay, and here's a calculation that I'm just going to leave up, let you work through, take a look at. It's simply using the equation, determine delta G, free energy, at 298 kelvins room temperature, for the reaction below if the K value has this number. The K value has this number. So what do? Free energy. What do we need to know? We're looking for delta G. We're given K. We're given temperature. And R is a constant. Nothing else matters. R, the temperature, natural log of K. And you just calculate it through, and you can find the free energy. Is this reaction spontaneous or non-spontaneous? It is non-spontaneous to the tune of 31.5 kilojoules. 31.5 kilojoules. Not spontaneous, does not want to go freely on its own. Is this a huge number? Not like the ones we looked at earlier, where it was like 1,300 and 1,400 negative delta G. Those were incredibly spontaneous, lots of energy involved. This is not a huge amount of energy. Okay, here's one last problem. I'm just going to leave this here and let you work through this on your own. You can pause the video and take a look at it and work it through. Okay.